So as we talked about at the end of the last lesson, is that as a reaction continues, the concentration of the reactants tend to drop because you're using them up, and that because of the fact that the rate of a reaction is highly dependent on the concentration of the reactants, then the reaction rate changes, or specifically the instantaneous reaction rate changes. That is the reaction rate at some particular point in time, like the reaction rate at that point, or the reaction rate at that point. Here, the reaction rate is a little higher, but there it's not as steep, so the reaction rate's a little bit lower right in there. And so it would be quite useful to be able to find the reaction rate for a reaction based on the concentration of the reactants. And we can do this by using something called the rate law expression. Typically, it's more common for people to call this the rate law. And so let's take a look at this rate law expression. So suppose we have a chemical reaction where substances A, B, and C are reactants. So we got something where it's like, A plus B plus C yields, dot, 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 something like this. The rate law has the general form that the rate is equal to K times the concentration of A to the X power times the concentration of B to the Y power times the concentration of C to the Z power, where rate written out here is the instantaneous reaction rate in molar per second. Okay, so that's the instantaneous reaction rate. K is what we're going to call the rate constant. Okay, and the units of the rate constant vary based on the reaction order, which we'll talk about later. Okay, so that's what K is. Concentration of A, concentration of B, concentration of C are the concentrations of each reactant specifically at the beginning of the reaction, whenever the reaction starts. And the exponents X, Y, and Z are what we call the orders of the reactants. Okay? So normally if we were trying to say what is X, we would say X is the reaction order with respect to A, and what is Y? Y is the reaction order with respect to B. Okay? So here's what these mean. Because it's like, what do you mean by an order of the reactant? What does that mean here? Well, an order of 1 means the rate is directly proportional to the concentration of that reactant. So if, Z right here was a 1, that means that if I doubled C, then the rate would double. If I tripled C, the rate would triple because it's C to the first power, and C to the if the concentration of C was twice as much, 2 to the first power is just 2, so it just doubles. If the order was 2, so instead of being a 1, it's a 2 is the reaction order with respect to C, then it means the rate is proportional to the square of the concentration. So if I doubled the concentration of C, then the reaction rate would quadruple. If the reaction order for Z, if it was for C, that is Z is, if it was like 4, that would mean that the reaction rate would increase to the 4th power with the concentration of C. So that if I double the reaction, then the rate would increase by 2 to the 4th power. And that's how much the rate would increase by. It's also possible, it also is possible to have a reaction order of 0, a 0th order reaction. And if that were the case, this would just be like, let's say Z was 0, we would have C to the 0 power, the concentration of C to the 0 power. And if you remember from your math stuff, anything to the 0 power is just 1, which means that the concentration of C does not affect the reaction rate. It has to be present, because if there was no C, there'd be no reaction. But if there's any bit present, then the reaction will continue, but it has no basis. I double the amount of C and the reaction rate stays exactly the same. Those aren't common, but they do exist. So those are basically what we mean by the order of the reaction. So these reactant orders, they cannot be derived. There is absolutely no way that we have to be able to look at, let's say, the balanced chemical equation or the types of substances that are there to figure out what the reactant orders are. We have to do it experimentally. You have to take a reaction and you have to, do that reaction, measure what the rate is at different concentrations, and I'll show you how to do that later on with this method of initial rates. But you have to do it experimentally. So, second thing. If you add up all the orders of the reactants, that's the overall reaction order. So this overall reaction order for this particular equation down here would be simply X plus Y plus Z. Okay, and so that's what we call the overall reaction order. I guess I said it down here. So We can use this overall reaction order to find the units of the rate constant K, because you remember we said that the rate constant's units vary based on the reaction order. Well, that's what we mean by reaction order. It's basically the sum of all the orders of the individual reactants. And so here's how we figure it out. The units of the rate constant are always the good old-fashioned molar per second, like we've said. That's our rate unit right here, divided by the molarity to the overall reaction order power. So let's say that we had a reaction that was that the rate law looked like this. So K times A times B squared, like this, b to the second. The reaction order with respect to A is 1 because there's an implied 1 right there because it's just written as A. The reaction order with B is 2. The overall rate order would be 1 plus 2 is 3. So that's going to be our overall reaction order. So if we wanted to figure out what the units of the rate constant would be, we would say it's going to be, all right, molar per second divided by molarity to the third power. And so what's going to happen here is that there's a little molarity on the top. That's going to cancel that 3 out and turn it into a 2 just by good old algebra here. And so if I did this, now I have 1 over seconds on top. I have molar squared on the bottom. And so this would just turn into 1 over molar squared times seconds. Right, like that. So we can sort of go through what the different reaction orders would look like. So if we had a reaction order of 0, this would just be, molar per second over m to the 0 power. That's just 1, so it's just going to be molar per second. If the reaction order was 1, then it would end up being molar per second over m to the first power, in which case the m's would just cancel, and so it would just be 1 over seconds. If the reaction order was 2, then it would be this over molar squared. The mole would cancel out the 2 and leave just 1 molar on the bottom. So it would be 1 over molar times second. 3 we just figured out. We already got that one. 1 over molar squared times second. So you can see there's some weird units. They look very different depending on what the reaction order is. You just sort of have to follow our particular little equation guy here to figure out just what that is. This molar per second divided by the molarity to the overall reaction order power is going to give you the units of that rate constant. So let's take a look. So we have this reaction right here. 2NO plus 2H2 yields 2N2 plus 2H2O. And so let's suppose that we did an experiment and we found that the rate law was this: K times NO to the concentration of NO to the second power times the concentration of H2. So let's go through our different pieces here. First thing, the order of the reaction with respect to NO. There's a 2 right there. So that means the reaction order is 2 for NO. For H2, there's no exponent, which implies that it's a 1. It's like, did you say x? That means it's x to the first power. So that means the reaction order with respect to H2 is 1 right there. Now, overall reaction order is going to be the sum of the 2. So 2 plus 1 equals 3. So the reaction order is 3. The units of the rate constant K, so because of the fact the reaction order is 3, it's going to be molar per second. That's a second right there. Divided by molarity to the third power, because the reaction order is 3. The m is going to cancel out the 3, turning it into a 2 right there. And so that means we just end up with 1 over molar squared seconds for our unit for K. And so that's how we end up getting 1 over molar squared seconds right there. Let's take that same reaction, same rate law, and let's take a look at how what the rate would do based on this. So let's suppose that we doubled the initial concentration of the NO, of the nitrogen monoxide, and we said, what's going to happen to the rate? Well, because of the fact that the order of the NO is 2, that means that if we whatever we change for nitrogen, for the nitrogen monoxide's concentration, the rate is going to change by that amount squared. So if we double the concentration of NO, the rate is going to change by 2 squared. And so that means that the concentration, the rate is going to go up by 4 times right there, because of the fact that the reaction, the order with respect to nitrogen monoxide is 2 right there. What if we double the concentration of H2? Well, the order with respect to H2 is 1, which means that it's a straight, direct relationship. So if we doubled H2, then it would just be 2 to the first power. That's just 2. So it would be 2 times. So the rate would be twice as high if we double the concentration of H2. Okay, let's get a little fancy. What if the concentration of nitrogen monoxide was halved, but hydrogen gas was tripled? Okay, well, this one, let's look a little more closely at this. So we know that the nitrogen monoxide is going to be to the second power, and so since that's being halved, we could just do it sort of this way, 1/2 squared, times the H2 is to the first power, so that's going to be tripled, right, like this. And so 1/2 squared is 1/4. 1/4 times 3 is 3/4. So if we were to halve the concentration of the nitrogen monoxide, triple the concentration of H2, we would expect that the rate would be 3/4 as big as it was originally. Right there. So you can sort of see how we can use our rate law to figure out how that rate changes, to find out that, hey, we double the concentration of NO, the reaction is going to happen 4 times as fast, at least to start with. And if we double the concentration of H2, it's only going to go twice as fast. But if we halve the concentration of NO but tripled H2, the reaction would only proceed at about 3/4 the rate that it did before. So it wouldn't be quite as quick as it was otherwise. So few notes about this rate constant. First thing, rate constant's K. Don't confuse it with KEQ like we saw in equilibrium. They're not the same thing. They look like they're both lowercase k's. They're both constants, but they're not the same thing. So just watch out for that. Next thing, the rate constant is different for each reaction. Okay, so if you had, a reaction that's like, H2CO3 decomposes into H2O plus CO2, is that reaction would have a particular rate constant K, though that rate constant does vary if the temperature of the reaction changes, because we know the temperature can affect the rate, or if a catalyst is added, or if there's already a catalyst if it's removed, so a change in the catalyst. But if I have this reaction, H2CO3 yields H2O and CO2, and the temperature stays the same, and no extra catalyst or no change in the catalysts, then K will always be the same for this particular reaction. Whatever number you get for K for that rate constant, it'll always be the same for that reaction at the same temperature with the same catalyst, which is going to be a lot of the time when we do this here. So the rate constant does not change for a particular reaction as the concentrations change, as long as the temperature stays constant or a catalyst is not added. Now, the key to what this means down here is that if we can find K at a particular point in a reaction for a particular reaction, then we can use that same K any time for that reaction as long as there's no temperature catalyst change. So when we went, if we can basically figure out the rate law, figure out what the rate constant is, we can reapply that for that particular reaction, not for a different reaction, but for that particular reaction all day long, any set of initial concentrations, we can then for that particular reaction figure out what the rate's going to be. Okay. The rate constant, as we sort of said, like the rate law, does have to be determined experimentally. There's no way to figure it out. You can't figure it out from the coefficients or from the bonds or the bond energies or anything like that. You just gotta do an experiment. Now, okay, so you want us to do experiments here. Let's take a look and see what this would look like. How exactly do we find the rate law? How exactly do we find the rate constant? And so we'll use something called the method of initial rates. And so to use this method, what we do is we perform several experiments. You measure the reaction rates at different concentrations, but you only vary one reactant's concentration at a time. So let's suppose I have this reaction. So I'm going to react A and B to produce X and Y. And so A is a reactant, B is a reactant. So what I'm going to do, experiment 1. I'm going to put in a certain concentration of A, a certain concentration of B, and I'm going to measure what rate I get. For experiment 2, I am going to keep the concentration of A exactly the same as what it was last time, but I'm going to change B. I'm going to change B probably by doing something like doubling it, maybe tripling it. Hopefully a simple one. You can do it if it's more complex, but it makes it a little easier to use this. If this was like, if that were 2 was the original concentration, I'm going to make this one 4 molar like that. That'll make it really easy. And then I'm going to measure the rate again. So I'm going to get a different rate the second time, probably. And then I'm going to go back and I'm going to do a third experiment. In the third experiment, I'm going to go back to the original concentration of B. I'm going to keep that, put that back what it was originally. But what I'm going to do is I'm going to change A. And so if the first A was 1 molar, the second A would be 1 molar because I kept those two equal. But the third A, I'll do something like double it, like this. And I'm going to measure the rate. Okay, so what I'm doing, I'm just changing one thing at a time and figuring out and measuring what that initial reaction rate is, what it is to start off the reaction. And so when you do that, let's take a look at what we could get. So we did experiment 1, experiment 2, experiment 3. Notice that for experiment 1, we had a concentrations for the 0.2 and 0.1. We got our initial reaction rate. For experiment 2, we kept the rates, the concentrations to start with the same for A, but we changed the concentration for B. We made it twice as big, and we measured the reaction rate. And then for experiment 3, we then changed the reaction rate. We doubled it going from for A, but we kept B the same. So this B stayed the same right there. And we found the reaction rate. But I want you to look at something very carefully. First experiment, we doubled B, right? B is now twice as large. Look at what happened to the reaction rate. It went from 1.0 times 10 to the negative third to 2.0 times 10 to the negative third. The reaction rate doubled when we doubled B. And what we said is that if whenever you change the concentration, if the rate changes by the same amount, that means that the reaction order is 1, because 2 to the first is equal to 2. So the rate, if I double the concentration, it doubles the reaction rate. The reaction order has to be 1. So when we write out this rate law for this, we're going to go ahead and say that B is 1. Is the reaction order here. Really, we just put B here. We don't have to put the 1. But so this is what we have so far. We still don't know what the reaction order for A is, but we do know it for B. So let's figure out what it is for A. So looking at A, now we're not going to care about 2 anymore. 2 is sort of irrelevant because we didn't change A for 2. But we're going to look at 1 versus 3. So we doubled the concentration of A. Let's look at what happened to the reaction rate. It went from 1.0 times 10 to the negative third to 8.0 times 10 to the negative third. It went up by a factor of 8 times. So the rate went up by 8 whenever we doubled the reaction, whenever we double the concentration. So the question is, 2 to what power equals 8? Well, 2 times 2 is 4. 2 times 2 times 2 is 8. That's 2 to the third power. And so that means that the order of the reaction with respect to A is 3. So we can go ahead and put a 3 in. So now we have a large portion of our rate law. We can say rate is equal to K times A concentration of A cubed times the concentration of B. So what about the rate constant? Well, once we know what the basic form of the rate law is, we can just take the numbers for one of these and just plug them in. Because what we're going to do is we're going to say, well, the reaction rate, we're going to put that in for the reaction rate. And we're going to take the concentration of A, and we're going to put that in as the concentration of A. And we're going to take the concentration of B, and we're going to put that in as the concentration of B right there. And just see what we get. And so when we do that, we have, 1.0 times negative third equals K times 0.2 cubed times 0.1. We can multiply these guys out, get this right here, solve it, and we find that K is 1.25. We could have done the same thing with the numbers from reaction 2 or reaction 3. We'd get the same result right here. And so we know K. We do need the units on K. So to do that, we do have to look at the overall reaction order. So it's going to be 3 plus 1. Whoops. So 3 plus 1 is 4. is our reaction order. So it's going to be molar per second divided by molar to the fourth power. The molar cancels the 4, so that turns into a 3. So then it's going to be 1 over molar to the third times seconds. And so 1 over molar to the third times seconds. So K equals 1.25 times 1 over molar to the third times seconds. And so that's going to be what our K is. If we had to write out our overall rate law, then the rate would be equal to 1.25, 1 over molar to the third seconds times A cubed B. And that would be our rate law. And now, once we have that, we can say whatever concentration we want for A to start with, whatever concentration we want for B to start with, we can put in those concentrations and calculate what the rate is, right like that. So let's take a look. So we now know the full rate. This is the same reaction here. So you see we have our same rate law as we did before. So we're going to find the reaction rate for any concentrations, as long as there's, once again, no temperature change, no catalyst change. We change the temperature, all our bets are off because K is now different at that point. So for the following reaction, what is the reaction rate if 5 moles A and 5 moles B are placed in a 10-liter container? So this is how we're starting it here, 5 moles A, 5 moles B. Well, we can go ahead and find our reaction rate, or find our concentrations. So for A, concentration is going to be moles per liter. So 5 moles of A per how many liters we have here? 10-liter container. So the concentration of A is 0.5 molar. Concentration of B, we also put in 5 moles, also in a 10-liter container. So concentration of B is going to be the same thing. Is also going to be 0.5 molar. So now what we're going to do is put it into the rate law. So the rate law says the rate is going to be equal to 1.25 times the concentration of A, 0.5 to the third power, times the concentration of B, which is also 0.5 to the first power. Now we just have to do the math right here. And let's see what we get. We multiply those guys out. I get 0.078125 molar per second because it is a rate. Sig fig wise, we've got 1 sig fig out on like everything here. So it'll just be 0.08 molar per second is our reaction rate for starting the reaction with 5 moles A and 5 moles B in a 10-liter container. So we can find that instantaneous reaction rate just like that. So let's try another one. Find the rate law for the following reaction in data. So H2O2 plus 3 iodide ions plus 2 H plus ions. An aqueous solution gives us 2 water plus 3 I minus right there. So a little bit of interesting reaction, but we're still going to work out the same way we do. We have 3 different reactants, and so that means our rate law in general is going to be the form K times the concentration of H2O2 to the X times the concentration of I minus to the Y times the concentration of H plus to the Z. All right, so now we've got to figure out what is X and what is Y and what is Z. So first one here, let's take a look. Looks like we kept I the same from experiment 1 to 2, have H plus the same from experiment 1 to 2, but we did double H2O2, and we doubled our concentration of H2O2, the reaction rate doubled. And so that means that the power, the rate with respect to H2O2, the order of respect to H2O2 is going to be 1. And so we can go ahead and put a 1 up there for that one, because when we doubled the concentration, it doubled the reaction rate. Okay, so then we go to our next one here. So the next one that changes is going to be the I right here. So we also doubled that. When we doubled that, what happened to the reaction rate? It went from 4 to, can't read it because I just covered it up, but 4 to 8. Again, or 4 times 10 to the negative third to 8 times 10 to the negative third. So that also doubled. So when we doubled the concentration of this, it doubled the reaction rate, and so that means that that's also going to be a reaction order of 1. Last one is our H plus ions. And so for those, we going from here to here, doubled it again from 0.1 to 0.2, double the concentration. Let's look what happened to the reaction rate. It went from 4.0 times 10 to the negative third to, the same thing, 4.0 times 10 to the negative third. So when we doubled the concentration of our H plus ions, there was no change in the reaction rate. And if there's no change in the reaction rate whenever you change the concentration, that means that the order of the reaction with respect to H plus is 0. So 0 is our reaction order there. So our overall reaction order is going to be 1 plus 1 plus 0. Overall reaction order is going to be 2. If we had to write out our rate law for right now, we're going to get that rate equals K times H2O2 concentration times I minus concentration. But since this H plus is the 0 power, anything that's 0 power is 1, we don't even have to write it down here, so we don't include it in the rate law. So it's just going to be K times H2O2 concentration times I minus concentration. Now we got to find K, we got to find our rate constant. So we're just going to take the numbers from one of these. I'm just going to use the first one, might as well, plug it in, see what we get. So the rate for that one is 4.0 times 10 to the negative third equals K times the concentration of H2O2 is 2.0 times the concentration of I2 is 0.1. We don't have to worry about the concentration of the H plus because it would be to the 0th power, which makes it just 1 anyway. Now we just got to solve for K. 2 times 0.1 is 0.2, so let's divide both sides by 0.2. And so when I do that, let's see, what do you end up getting? I end up getting right at 0.02 is what I get for K for the rate constant. Unit wise, it is going to need to be, let's see, it's molar per second divided by molar to the rate order, which we said is 2. Right there, second power, that molar cancels that one out, so it just ends up being 1 over molar times seconds right there. And so 1 sig fig, we can't have less than that, so that's, and actually, do we have one? Nope, it's going to be 2 sig figs, because all the numbers that we had here all had 2 sig figs that we used, and so this actually is going to be 0.0201 over molar seconds for our overall rate constant. I guess that means that we do need to include that in our overall rate law. And so to get our final rate law here, I'll rewrite the one at the top up here. We're going to get rid of that because that's the 0th power. It just goes away, turns into a 1. We got those two right there. I don't even have to write the ones on there because anything to the first power is just itself. Then we said 0.020 equals the rate. So the rate law here, 0.020 times concentration of H2O2 times the concentration of I minus. All right. So sometimes you have to do all this sort of in the background. It doesn't ask you directly for the rate law. It just asks you for the rate. Then you have to find the rate law and then use that to find the rate. So here we have substance A is decomposed to form B and C by the following reaction. 3A yields B plus 2C. What's the overall reaction rate when the concentration of A is 5.0 molar? All right, so we need to figure out what is our rate law so we can find the reaction rate. Now we know the rate law is going to have the general form that rate is equal to K times the concentration of our first one, which is A. And that's it, right? Because there are no other reactants. It's just A. So A to the X. So we'll just have to do it that way. It does make it a little easy because there's only one thing to change. So what do? We increase the concentration of A by a factor of 4, and what happened to the reaction rate? Ooh, those aren't nearly as pretty. Can't really do that in our head, but we can still figure it out. What you simply want to do is you'll take, your final one, 1.24 times 10 to the negative second, and divide it by 7.77 times 10 to the negative fourth. By doing that, that'll tell us how many times it's increased by. And so let's see, when you do this, I end up getting that is 15.96. And you're like, well, if we increase the concentration by 4, the reaction rate increased by 15.96. That's a little weird. It doesn't seem like it'd be a whole one, but if you actually look at this, 15.96, that could be within the range of our error. You know, there are only 2 sig figs on this measurement right here, the 3 on this one right here. And so, you know, this is very clearly going to be 16. And 16 is 4 to what power? So it's 4 squared. And so that means that since 4 squared is 16, because really that's what we're doing, we're saying 4 to the x equals 16, so it has to be a 2 right up there. That means that our x is going to be 2. And so the order of the reaction with respect to A is 2. So we got a rate of K times A, concentration of A squared. Now we got to find what our rate constant is. So we go ahead and say the rate, 7.77 times 10 to the negative 4th, equals K times the original concentration, 1 molar, to the second power right there. And so all we have to do is just go ahead and do that math right there, where we say, let's see, oh wait, heck, 1 times 1 to the 1 squared is just 1, so that means K is equal to just 7.77 times 10 to the negative 4th. Well, that was sort of silly. And so that's equal to K. Now we just need our unit. Let's look at the order of the reaction. Well, the order of the reaction is just 2, so that's going to end up being, if we look at this here, 1 over, sorry, not 1, molar per second over molar squared. This m cancels that right there, so it ends up just being 1 over molar per second right there. And so that's our constant. And so putting that into our overall equation right in here, we're going to end up getting a rate law of rate is equal to 7.77 times 10 to the negative 4th. That's negative 4th. A squared is going to be our rate law. So now we have the rate law, we can go ahead and solve the problem. The question is, what's the overall reaction rate when the concentration of A is 5.0? Well, now we know the concentration, we can plug it in for A, and we're good. So rate is equal to 7.77 times 10 to the negative 4th times the concentration of A, which we said was 5 molar, squared. And so all we got to do is say 5.0 squared here. So it's 25 times 7.77 times 10 to the negative 4th. And so when I do that, I get a rate of 0.019425 molar per second. Sig figs wise, the only real value we sort of used here, we had the 2 sig figs here, 3 sig figs there, 2 sig figs here. We're all doing multiplication division across the whole thing, so it should be 2 sig figs. So our final answer here is going to be 0.019 molar per second for our overall reaction rate, our initial reaction rate, if we made the concentration of A 5.0.